Okay, we have another example. It's example 4.4. In this example, a frame supports part of a roof of a small building. The tension in the cable is 150 kilonewtons. And we're supposed to determine the reaction at the fixed end E. Okay, so we're trying to figure out what's going on right there. Okay, so we need to draw a free body diagram, right? So what does our free body diagram look like? Well, we have this object, and it's an object like this. Okay, and then you have something coming off here. Okay, now I'm going to cut this free body diagram. What I'm going to do for my free body diagram is I'm going to go right through here and through there. So whenever I cut through something, I need to replace it with an unknown force that's appropriate for it, right? So here, I cut through there, so I'm going to have an unknown force, and this is going to be, I don't know what, this is going to be tension, T, and that is equal 150 kilonewtons, right? And it's in a given direction. Now we have the forces that are applied here, 1, 2, 3, and 4, just like the picture, right? And then here, when I cut through this thing right here, what did I cut through? What can that resist? Well, it resists a force in this direction and in this direction, but also it resists a moment. Now I am arbitrarily defining the direction of these things, and actually, quite frankly, I just saw that my x direction is going to be wrong, and we'll talk about that in a little bit, but that's fine. It just means I'll get a negative number. My moment, I have no idea, and we'll see how it goes. Okay, so what are our equations? Well, you have the sum of the forces. I'm going to over and over and over. Sum of the forces in x equals the sum of the forces in y is equal to 0. And you have your sum of the moments is equal to 0. So which one should we start with? Well, in this case, I would say let's start with the sum of the forces in y. Let's even go beyond that. Let's start with the sum of the forces in x, because there's only one force that has a value in x. And so let's say, okay, therefore the sum of the forces in x is equal to 0. So what do you have? You have your tension in the x direction plus, this is point E, so this is EY, this is EX, and this is moment at E. That's an X. I know it looks like a Y. So the way I drew this, and you just got to be consistent with how you do it, TX plus EX is equal to 0. Therefore, EX is equal to minus TX. Well, do we know what TX is? Yeah, we do. It's a triangle here. I'm going to skip over here. Well, let's do the triangle right here. We have this triangle, right? And so for this triangle, that 2.25 plus this distance is 2.25 plus 3.75, so that's just 6. And we take the sum of the squares of 4.5 squared plus 6 squared. This value right here ends up being 7.5. Okay? So our t in the x direction, you could say t times the sine of that theta, but what is that really? It's just 4.5 over 7.5, right? So this is equal to t, so minus 150 times 4.5 over 7.5. Okay, therefore our e in the x direction is equal to a negative 90 kilonewtons. Which just means what? It means it's in that direction. Okay, so there we go, our e in the x. Now let's do the sum of the forces in y, because that seems like it's a good thing to do. So sum of the forces in y equals 0. Well, in this case, each one of these is 20 newtons. So you have 20, and there's 4 of them, right? So there's 4 going down of 20, and then you have plus your t in the y direction. So all the downs equal the ups is going to equal the EY. Okay, so you have 80 plus, what is a TY? Again, it's 150 times the cosine, which is going to be 6 over 7.5, is equal to EY. So therefore, EY is equal to 200 in that direction. Okay, just for clarity, when I did this over here, this EX, it might be more accurate to say EX is equal to 90 kilonewtons in that direction. Okay, and so what's left? Well, we still have one unknown left, and that's the moment at E. So is there a moment at E? Well, this thing is buried straight in the ground, so it has the ability to resist a moment, so we got to figure out what that moment is. So how do we do that? Well, let's take the sum of the moments. And where should we take them? Honestly, it doesn't matter, but E is as good a place as any, so let's take the sum of the moments about E is equal to 0. So what do you have there? You have 20 times the 1.8, and there's times 4. This is just the distance right here. I just don't feel like figuring it out, right? And then we're going to add 20 times 1.8, and there's 3 of those, plus 20 times 1.8, and there's 2 of those. So this 1, 2, 3, then plus 20 times 1.8, and there's just 1 of those. So those are all the forces that are making this thing rotate counterclockwise. And then we have the minus, sorry, I'm going to have to carry on to the next line, minus the t in the x direction times this lever arm, which is 6, right? That's going to make it rotate clockwise. And what about the t in the y direction? What's the lever arm in the t in the y direction? Well, it passes straight through E, so that is a non-issue, so that gets to go away. So that's 0. So what's missing here? In this case, I need to add in plus my moment at E is equal to 0. So why did I add the ME? Because quite frankly, when I drew my arrow up here, I arbitrarily picked a direction, and I happened to pick it in the same direction as what these forces are going to do. So you just have to be consistent. Once you pick up something, be consistent, stay married to it till you're done, and then you can figure out if it's in the wrong direction. Okay, so there we go. We got that. And we know t and x. We know all these things. And so it turns out that you can just solve for the moment at E is equal to 180 Newton meters, which means it is again, to be clear, you can say this. It's 180 Newton meters counterclockwise, or in that direction. Sorry. And that is your moment. So there you go. You solved for it. You have your EX, EY, and the moment at E. And those are all the unknowns that you have.